What happened? Oh, no problem, man. Thank you, Couch. Okay, so here is cyclohexane, yes? We're doing cyclohexane chair conformation. You can have something like this, which this is a CH3, and this is a CH3. And what is that? Is that cis or is that trans?
It's cis.
You have to know that both of these are on the same side, yes?
Mm-hmm.
So when you draw this, if I place a CH3 here, where's the other CH3 going to be at? Hello?
On the
So
other,
this is upper bond,
on the
lower
epithelial.
bond. If it is to be cis, it has to be in the lower bond. Since this is 1, 2, the other CH3 has to be here. You are expected to know how to determine that. Okay? And when we are doing determine the stereochemistry there. Determine which one is R and which one is S. Write it down. No, let's try it with this, man. You don't dirty your stuff. Let me see. Throw it. I'm getting older, I guess. See if you can catch me.
Ooh!
Man, it's on fire.
Great.
All right. So this here is a chiral center because it has 4 different groups on it, yes? And what is this? Is this R or is this S? I mean, just say S or R, okay, if you don't know. So we have to assign priorities, yes? So you guys had a problem assigning priority?
No.
It's really S, but it should be R, right? Because the lowest group is pointing forward.
Change the structure. What was it that I had written? Okay, so we assign priority, yes? Which one is the highest priority?
BR.
No.
For that what power?
You have to assign priority here, here, there, and there.
CH3.
CH3 is the highest priority?
No.
Absolutely not.
Oh, the one that has
Is this the highest priority?
triple carbon.
No. Okay. Here's a CH2 and here's a CH2, yes? So you can determine it based on that. You go to the next one. Here's a CH2 and here is a CHBr. So this side has a higher priority. Okay? So this is priority 1. This is priority 2. This is priority 3. And this is priority 4. Okay? So what rotation is this? Is this clockwise or counterclockwise? What else do we have to do?
You have to rotate the hydrogen.
This hydrogen is supposed to be where? In the back. It's supposed to be in the back. It's not in the back. It is in the front.
So it's really a...
So when we look at it, because this is in the front, we can find the rotation and then it will be the reverse of what we are looking at. So this rotation seems to be R. But it's not R because this is in the front, so this is S. Okay? Okay, you try for this one now. Okay. Which one is the highest priority?
Bromine.
Second?
Over there, that side.
This one?
Yeah.
Good. And?
The other one.
Third? And? Fourth. That hydrogen happens to be in the back, yes? Since it is in the back, we are just going to read it. So this is
S.
1, 2, 3. This is
S.
S. This is counterclock, this is S. You guys ever seen that before? Yeah, that's a benzene ring. You never seen this before?
Yeah.
Maybe some of you have done this before. This is amphetamine. Okay. And you want crystal meth? Crystal meth is called methamphetamine. One of the hydrogens has been replaced with a CH3. How's that? Now find the enantiomer of, let's find it of this one. The amphetamine. This is methamphetamine because of this methyl group here. And of course, everyone knows what methamphetamine is, right? crystal meth. If you look at the structure of pseudoephedrine, epinephrine, you ever heard of that before?
Yeah.
This what is it used for?
Epinephrine?
Yeah.
Like allergies. Like if you go on.
What is it called? No. Sudafed, my friends.
Oh, Sudafed. Okay.
It's for the nasal decongestion. It's for nasal decongestion. This nasal decongestion, if you look at the structure, is very similar to that. So you can make this methamphetamine from that thing. So if you go to the pharmacy, they ask you for your license. So they can know who you are. Maybe you want to buy, maybe you want to make methamphetamine. So I'm going to erase this one, okay? So what is the enantiomer of this? Is this R or S?
R.
Hello?
R.
So which one is the highest priority?
The hexane.
No. Hexane, highest
Yeah.
priority. Highest priority is
And it's
nitrogen.
yeah.
Yes?
Yeah. It's S.
Next.
Right.
This one. Yeah.
And next,
Yeah.
3.
Yeah.
And this
S.
is the fourth priority.
S.
This is going to be,
So it's
S.
S.
is this hydrogen in the back?
Yeah.
Yes, hydrogen is in the back.
Professor, why is that one second priority?
Because it's on the second, the hexane on the second carbon, right? Not the first?
No, it's not because of this. It's because this carbon here has 2 hydrogens and
Next guy.
another carbon, while this one has 3 hydrogens. Yes? So in a way, the 2 hydrogens from both of these cancel out. So you go to the next one, and it's a hydrogen and a carbon. So which one wins? The carbon. So this is why this is a higher priority. The less hydrogens it has, the higher the priority. So here, so how are we going to rotate this? This is rotating S or R?
S.
Very nice. So if we want to draw the other one, what do we do? You can draw the mirror image, or you can just,
Change. Okay.
what would you like to change?
The CH3 on H.
The A's and the CH3.
Mhm.
If you do that, let's count this again. This is priority 1, priority 2, and priority 3. Well, this is 4th priority. So I am going to go 1, 2, 3. It looks like that, yes, but the hydrogen is in the front. So,
So now
it
it's
looks S,
R.
but it's not S. It is
R.
R. And you can, of course, draw the mirror image of that. Which we did last class. Is anyone confused with these 2 things and these 2 things being in a different place? What is your confusion?
When you asked to draw the mirror image, what are you switching?
You're not switching anything, you're drawing the mirror image of that.
So it's just
It is
facing
like-
each other like that?
Why is it supposed to be S but it's R? Just because the hydrogen's in the back? Or it's,
In the front, in the mirror,
where's the hydrogen supposed to be?
in the
In the
back.
back? In the back?
The lowest priority is in the front.
Sophia, you have not studied, my friend, have you? Do you need some methamphetamine? Yes, for those of you that have not studied, the hydrogen has to go in the back. Or the lowest priority has to go in the back. It might not be a hydrogen at times. It might be a CH3, but it has to go in the back. If it's not in the back, and if it is in the front, you have no problem. You just look at it and it will be the reverse of what you see. But if it is here or here, the hydrogen, you do not do it like that. If it is in the ones that are on the same plane like this, if the lowest priority is, let's say, it is like this, what do you do here?
You just count it.
If it is like this, highest priority, 1, 2, 3, and 4. Do I go 1, 2, 3, and I say this is S? Is that what I do?
No.
It's R.
It's R?
It's R.
What I said? I said, if it is on this bond or on this bond, you do not do it like this. If it is in those bonds, you are going to change it and make it in the back.
Yep.
Yes?
Yes.
Hello?
Yep.
Yes.
So what you are going to do, if the hydrogen is here, I am not even going to try to do it. What you are going to do is redraw it. And this time you are going to exchange what by what? You are going to exchange what I need to be in the back for whatever is in the back. This is in the back, and I am going to exchange it for this. Everybody else is going to stay the same, yes or no?
Yeah.
So this is going to be 1, 2, and 3. This is S. So if this is S, this one, which is the enantiomer of that, is the reverse, because I exchanged two groups, must be R. But we decided it was S before, didn't we?
Yeah.
And I am going to tell you, I will sit down and think about it. So if you try to play games, you're going to get it wrong on the test. Okay? I'm going to make one that is not what you expect. So you learn. If it is either here or here, on this plane, you change it and put it in the back. Okay? It doesn't bother me if you draw another structure on the test. That's fine. Okay? Any questions? Yes.
I remember a few classes ago you said priority is based on like the molecular weight,
Atomic number.
atomic number.
For the element that you are looking at, one element at a time.
So that's like bromines first, then
Yes.
So did you say that the more hydrogens, the higher the priority?
No, no, I said the reverse of that, Sophia.
The least priority?
This is what it is, okay? Let's say I have a bond here, a carbon here, and a carbon there. Can I decide?
No.
No, I can't decide. Let's say I have a hydrogen here and a hydrogen here. Can I decide?
No.
No. Let's say I have a hydrogen here and a hydrogen here. Can I decide? No. Let's say I have a hydrogen here and a carbon here. Which
Yes.
one do I decide? I decide for this one. Because when the time gets here, carbon and hydrogen, which one has a high atomic number? Carbon. That's when you decide. So you go one by one until you find a difference. Okay? Now we can draw another structure. It looks like this with, let's say, a CH3 and a CH3 there. This looks sort of like a hexane. Yeah, could be a pentose. This is a pentane ring, yes? 1, 2, 3, 4, 5. This is a way of drawing them. You can draw for 6, 2. Now, what you are going to look for when I give you a molecule is a plane of symmetry. If your molecule has a plane of symmetry, this has a special name. Does this have a plane of symmetry?
What do you mean by a plane of
Yes.
symmetry?
Yes, it does.
Opposite sides where
A
they're
plane of
mirrored?
symmetry.
Yes, it does.
Okay.
Does something cut it in half?
Half
And
and
one
then-
half is equal to the other half.
Okay.
Yes, there is a plane of symmetry here.
Here.
If there is a plane of symmetry, this center here, is this chiral? This center here is a chiral?
No.
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 What do you mean? It's,
No.
it's
You
not
have a
chiral.
hydrogen CH3.
Explain to me. Does it have 4 different groups on it?
Yes.
It has 4 different groups on it. And this one has
Carbon.
4 different groups on it too. But because this has a plane of symmetry, this is considered achiral. And it is achiral and called meso compound. And meso compounds have a plane of symmetry and are achiral. And I'm going to tell you what that means now. Sometimes the chiral center or stereogenic, have I mentioned that before, stereogenic? Chiral center or stereogenic center is one that rotates plane polarized light. Plane polarized light. So what happens is light is composed of a magnetic field and an electric field. And that field is oscillating in all possible directions. The field is going like this. Of course, it's supposed to go through the middle, but I'm bad at drawing these things, yes? This pizza is not looking good. Do you understand? The light is going all over the place, okay? Now, when you pass it through a polarimeter, you pass this light through a polarimeter, of course, this is in a tube. A polarimeter will have lines like this, and only one plane of light can pass through the polarimeter. So on the other side, you are going to have something called plane polarized light. Only one plane has that light. Now, if you pass this plane polarized light through a sample, and this sample is chiral, it will rotate plane polarized light, either that way or this way, yes? If it rotates this way, according to what you see, if you're standing in front of the instrument, if it rotates it this way, it's positive. If it rotates it that way, it's negative. If it rotates it in the positive way, it's called the dextro-rotatory. If it rotates plane polarized light in this way, it's called level rotatory. So D and L. That kind of makes sense, yes? The L stands for left. Okay, dextro-rotatory means it rotates things to the right, okay? The word dextro-rotatory means to the right. So, if you put inside of this instrument, which is plane polarized light, if you put a chemical that is chiral, it is going to do what?
Rotating.
Rotate plane polarized right, either to the right or to the left. Does this rotation have anything to do with R or S? No, it does not. I want you to write this down. This plus or this minus has nothing to do with R or S. You can have something that is R with this minus, or you can have something that is R with a plus. Write this down. Enantiomers have the same physical properties, and they cannot be separated by physical means.
Physical property of what? The same property.
By physical means, right?
And cannot be separated by physical means. I said enantiomers, yes?
Yes.
R and S are enantiomers, yes? Now, this here is a chiral center, yes? And it rotates plane polarized light one way, but this is the opposite, and it will rotate plane polarized light in the opposite way. As a result, meso compounds are achiral, called inactive in plane polarized light. Okay, so they do not bend plane polarized light. So, achiral compounds, do they rotate plane polarized light? No, they do not. Okay? But if you have 50% of R and 50% of S, 150% is going to rotate that plane polarized light in one direction, and the other 50% is going to rotate the plane polarized light. Is it in the same direction or in the opposite direction? In the opposite direction. If you have 50% of both, do you see any optical activity? That's what that's called, optical activity. When it rotates the plane polarized light, you do not see any optical activity if you have 50 of both. And this is called a racemic mixture. Good. Somebody read ahead of time, huh?
I want the one.
So it didn't come from you, huh? You could have lied, man. All right. So that is called a racemic mixture when you have 50% of each of them. There is something called an enantiomeric excess. Sometimes EE or lowercase ee. Enantiomeric excess is at times given in percentages. So let's say that something has 80% enantiomeric excess of, let's say, an R enantiomer. The question here is, how much of this is R and how much of it is S? Now, of that 80%, if you had R and S and they were the same amount, would we see anything? No. So 80% means that the other 20% is split half and half. Yes? That is why it did not rotate plane polarized light. So of this 20% that is left over, half of it is R and the other half is S. So how much is R? 10%.
10%.
And this 10% is S. Okay? So in reality, how much R do you have?
90.
You have 90% R, while you have
10%.
10% S. You need to understand what that means. Okay? Find. Oh. talk about this first. Want to talk about specific rotation?
No.
He doesn't like specific rotation? Specific rotation, or this alpha with this brackets in it, is equal to the observed rotation, just alpha, divided by the concentration times the length. This is observed rotation. This here is concentration. You guys did not want to calculate anything in this class, right? Maybe this is math.
Yeah, why not? It's even better.
I feel bad giving you math. Give me what? And this is the length of the tube of this. How do you spell length?
L-E-N-G.
Like this?
L-E-N before the G.
No, that's good.
Leg.
That's leg.
Okay, it's the same thing. All right, so on the test, I'm going to give you some numbers, and you are going to calculate the specific rotation for this, okay? I'm going to give you numbers like this. Oh, by the way, the length is given in decimeters. That's a problem, yes? Concentration is in grams
Per milliliter.
per milliliters. Okay? And this specific rotation, or the observed rotation, is in degrees. So let's do this problem. When a 0.300 grams, this is sample problem 5. Oh no, this is a different book. Is dissolved in 10 milliliters of water. And placed in a sample cell of 10 centimeters. The observed rotation is 1.99 in the positive direction degrees. So much writing. Using the D line of sodium, at 20 degrees Celsius, calculate the specific rotation.
The specific rotation.
Yes.
What's the unit?
I don't know, you figure it out.
Grams per milliliter.
Degrees.
Grams per milliliter.
Wait, what does that mean, the D line of sodium at 20 degrees?
I'm going to tell you in a minute, okay? Just do the calculation.
For the next test, do you bring a calculator?
Yes, for the next test, you bring a calculator just in case. Non-graphing calculator. So tell me, specific rotation is equal to what?
Alpha rho C
is equal to alpha, which is the observed rotation. Was that given to you?
Yeah.
Positive 1.99 degrees, yes? We are going to divide this by the concentration. The concentration in what? In grams per milliliter. We have to find that. That was not given to you. So all you have to do is, because this is so simple, you get the mass of this, which is 0.300 grams, and you are going to divide it by the volume, which is,
10.0.
and what does that give you?
0.03.
If you do this very complicated math,
0.03.
0.0300?
Just 0.3.
No, you got to keep the same number of significant figures. Is that right? You guys put in the calculator? Sure? Huh?
I got 0.03.
Yeah, of course, because the calculator is not very smart. The calculator is not very smart, and it believes that those zeros are not significant, so they just give you without the zeros. But since you are smart, you notice that those zeros go there, yes?
Yeah.
And you are going to write this number here. Yes? And you are going to multiply this by the length in decimeters, yes?
Yeah.
You got to convert from centimeters to decimeters. That's a tough conversion.
No.
I don't think you guys can do it. Can you do it?
Decimeters. 10.
You can?
You ready? My turn.
One decimeter is equal to 10 centimeters.
Divided by 10. 0.1.
1 decimeter is equal to 10 centimeters. So what are you going to do to make it centimeters? You are going to divide
By 10.
10 centimeters by 10 centimeters. And what are you going to get? 1 decimeter. That's very nice. That was not done by mistake. That was done on purpose. Of course, this was put here to confuse you, because somebody maliciously want you to get that wrong on the test. Okay? Yes, Karen?
Yes.
Malicious person wants to do that. Always me. If you do this calculation, what does it give you? This is a positive, yes? The positive is important because it is rotating plane polarized way. In what way?
D way.
Dextro-rotatory, to the right. So this is positive 60 what? 66.3. It has no units, my friend.
Oh.
Okay? You like that? Now, this D line here of sodium has to be included when we do the specific rotation. So here's how you write this. The specific rotation, down here you have to specify what you used, and what you used was sodium. Okay? Sodium was emitting light, and you used the light from sodium. That's why you have to put D line there. Okay? And on the top you are going to put the temperature at which you did this, because the temperature changes the specific rotation. Now, the temperature is not in the equation, is it? And sometimes it increases the rotation and sometimes it decreases the rotation. So we're just going to write it there. So when I give you a problem and I give you sodium, what are you going to put down here? The D. I don't know where the D comes from. Don't ask me. What if it's potassium? Right, Sophia? You feel like asking that. Oh, what if it's potassium, Professor? Do we write F? What do we write here? Don't say you did not have an urge to ask that.
Actually, no.
No?
But thanks. It might help later
Just
on.
in case. So, there's the D. I don't know where it comes from. When it's sodium, the D line of sodium, that's what you put here. And then up there, the temperature, and this will give you 66.3. Yes?
So we do put D even if it's potassium?
We will never talk about potassium. We only talk about sodium and the D line. Okay? So that always has a D as far as you know. Okay? Yes or no?
That refers to the line that it's passing through.
Yes, this refers to the line of radiation that is passing through coming from sodium. Now you do know that if you eat sodium, it emits radiation, yes? Okay?
Why is sodium used? Because of the lattice?
I got you started, huh? You were all quiet.
Yeah. What determines that it's dextrorotatory?
To the right.
The
To the
sun.
right. The positive
The
to the right.
rotation. Well,
And then the
the
left.
positive,
Oh.
what determines its next rotatory is that it will bend this light. You see, this is 0, yes? And if it goes like this, and this is 0, it bent it to the positive way. This is to the right. Yes?
Yes.
And of course, this thing here has little numbers, yes? Yes? Little numbers all over the place. This number here is going to be what?
Not 0. No. What do you mean? Are you rotating 90 degrees? What are you talking about?
66.3.
That looks like 90 from 0, no?
Okay, I'm going to tell you, okay? You guys have issues.
That's what I'm saying. It looks like 90. I mean, but
Looks like 90, no. It is 90. This is 90, and this down here is
180,
180. And this is?
270.
No, it is not. You made a mistake. That's minus 90.
Negative 90.
That's right.
Not minus.
Not minus? That's not minus?
It's negative.
Oh, because it goes in either direction.
So what's the 66.3?
Because it goes in either direction.
What is a
On
66.3?
that graph, like before that 90.
It's on
Let's
that
see.
side of the.
You count these little lines that I drew here until you get to 66.
Yeah.
Right here, right there, I counted
So why
66.
did you put the arrow forward?
It's an example. She asked, who asked about the positive thing?
But so in our case, that line would point to 66.
At 63.
I got your ass though. In all seriousness though, why is sodium just in case we're going to use it now?
Because I only know about sodium.
Or does it have to do with the structure of it and the light going through it?
It has nothing to do with that. It has to do with sodium is what is heated and it releases the light. That's what they use to pass it through the polarimeter and come out on the other side with plain polarized light through your sample and out the reading.
Does that all correlate with like shining light through a prism and then it emits different colors? Not good. Pink Floyd. Dark side of
Light through a prism. No, this is not like light through a prism. This is light through a polarimeter. I just drew the polarimeter, yes?
Yes.
Didn't I draw the polarimeter? I mean, it wasn't a nice drawing, but I show you light. I don't know if I should give you this other part. I'm not going to give it to you. You want it?
Yeah.
I don't know. I'm discouraged.
Professor, I have a question. What is the difference between an enantiomer and a diastereomer?
I have not talked about diastereomers yet. You will find out. Okay. Let's talk about.
Oh, so the one we just did was EE. Wait, or is that EE as well? Or is that CC? What? I'm kind of out. I just like 5 minutes.
Wait, is that paper?
Guys, be quiet.
Sorry.
What we just did was not called EE or CC or DD or TT. It's called specific rotation, what we just did. When we did previous to this, yes, it was this.
Okay, my bad.
No, that's okay. So, in order to calculate the EE, they should have used other letters.
Like TT?
Yes. Okay. So in order to know this enantiomeric excess, okay, I told you before what it meant, yes? I never told you how to calculate. So the way you calculate it is you put it through this polarimeter thing, and he'll give you numbers. Okay. In the book it says, I'm not going to write the whole thing, I'm sorry, okay? It says the specific rotation of optically pure adrenaline is minus 53 or negative 53, as she was saying. I guess that there is a very big difference between minus and negative, yes? So, pure is 53, yes? So let's say I want one enantiomer, and that pure enantiomer is negative 53. It says that they put a sample through and the observed rotation is negative 45. So this is I call it so this is for the pure sample, whatever we are looking at, and the other one is for the observed. What did I say before?
Negative
45.
Negative 45.
Observed is negative 45.
Negative 45. So if you had the pure enantiomer, that means either R or S. It doesn't matter what it is, but it is negative. And this is the observed. We are going to calculate the percent enantiomeric excess by dividing the little number by the bigger number, yes? Because if it was 100% pure, what number would you expect to get?
0. There's no excess.
100?
I'm not saying what percent do you expect to get. If it were 100% pure, what number would you expect to get here? Negative 53. Negative 53 divided by negative 53 times 100 would give you 100% pure. So, since it's not 100% pure, every expected number has to be lower than the pure. You don't even have to remember the equation. All you have to remember is you get the little number, divide by the bigger number, okay? Because it's a ratio. So here is going to be tell me what that is.
85%.
85%? This is 85% enantiomeric excess. You tell me, let's say, you tell me how much minus and how much plus you have.
In the pure or the observed?
What?
You're asking about the pure or the observed?
Yeah.
This is like the R and S thing, yes? But it's minus and plus.
So we're looking at 45 or we're looking at 53?
You're looking at the 85.
When you
Or
had
the
set the
85.
small, you
Ah, so you're
divide the
gonna
smaller
have-
number, you meant like the actual,
The observed, yes?
right? Because negative 53 is smaller than negative 45. So really,
So you're gonna
negative
have
53 over negative 45.
I meant to say the smaller rotation. I didn't mean to say,
The actual number.
yeah.
So you're gonna have 92.5 of one, and the rest is gonna be 7.5. Yeah.
Okay, so how much? So this is 85% of which one? Of the one that is
Observe.
negative, whatever that is, R or S, it doesn't matter. So 85 is the excess. So the rest of it, how much is it?
15.
15%. Half of that is negative, and half of that is positive. So this is 7.5 and 7.5. So in reality, of this negative, how much do I have?
92.5.
92.5? 92.5% is that level rotatory, we should say, yes? Guys, if you have questions, ask now, because I will never talk about this again.
Why did we decide that 85 was correlated negative? Because the observed value was negative?
That's not negative 92.5, right? Or is it?
Yes.
It is?
No, guys, this is not a, please, this is not a negative as it's a negative sign, yes? This means,
The direction that it's going in.
yeah, this is the rotation, right? This is not negative as in a negative sign and I add a positive sign. This is called, what is it called? Level rotatory.
And if it was positive,
Dextrorotatory, yeah.
And will we ever have a scenario where the pure is one way and then the observed is the other way?
No.
So whatever, they're both going to be facing the same direction, right? The pure and observed.
Yes, exactly what you're
So
saying.
then the percentile is always going to be the same sign as the numbers we're given.
Anything you say? What are you drinking there?
A naked.
A what?
Naked.
Naked? What does that have inside? Vegetables?
Yeah, this one's a protein, has 90% juice.
Okay, good for you.
It has a hint of pineapple and coconut.
I did tell you that normally you ingest 12 pubic hairs a year, yes? So how many do you guess that are in there?
You said fast food, it's not fast food.
That's fast food.
No, it took a long time to bottle it.
No, it didn't. All right.
Depends on who you are.
We talked about enantiomers, and now we're going to talk about diastereomers.
Can you say that again?
Diastereomers.
I'm trying to pronounce it.
There you go, guys.
Okay, diastereomers. Now, if you have on one center R and in the other one S, and they are total opposite of each other, they are called enantiomers. But if you have two chiral centers, and one is the opposite of the other one, and one stays the same,